Welcome back to Math 451. We're entering section 0.2. This is still supplemental to your textbook. We'll be looking at something called an algorithm. Algorithms are alternatives to formulaic solutions. You may have recalled back in your second quarter of calculus, you may be posed with an integral that you really couldn't solve. That didn't mean that the integral didn't exist. It just meant you couldn't solve it. The same kind of thing happened in differential equations, but we can still prove that a solution exists. The word algorithm has its origin from a book that was written by a Persian mathematician in the Middle Ages, but algorithms are much older than that. Euclid himself had an algorithm for trying to look for the greatest common divisor of two numbers, and that's shown on the left, courtesy of Wikipedia. And today, algorithms are the basis for all modern mathematical software. It is probably easiest to describe algorithms in terms of an example. Here you see a polynomial. It's a quadratic, x squared plus 2x minus 3. And what we want is to find out where that polynomial hits 0. Well, in this case, it's very easy to factor the polynomial into two terms, thus revealing the roots of being 1 and minus 3. So we know the answer to that problem. But how would you even solve a problem like this? X times e to the x equals 1. Give it a try. I think you'll have a lot more trouble with it than you might imagine. In fact, you really are not going to be able to come up with a formula that says x equals something. You could, however, write an algorithm that would give you a result. Even something simpler that you think you can do very easily would be a square root. How do you find the solution to x squared equals 5? Well, you'd say that's easy. That's plus or minus the square root of 5. But what is a square root of 5? So how do we solve these problems? All of them can be solved, including the one that's easy to solve on top, with an algorithmic approach, replacing formulas with algorithms. So how might we get started at developing an algorithm? The first step is to think through your logic using pseudocode. Maybe step one is really to do a little bit of preparatory math and then develop something we call pseudocode. A pseudocode is a kind of a mock language. It is never really intended to execute on a computer. What it does do is it allows us to think through logic, write it down in something that could later be translated, and have a basis for debugging the methods before we worry about debugging syntax. So let's take a look at our square root problem. We are going to rephrase this as the problem x squared equals a. So how might we find the solution to x squared equals a? So let's start off with a guess. Let's just suppose that we think the answer is 1. We'll call that initial guess x0. Now we will apply a correction to that guess. We'll take the number, square it, add a, and then divide by 2 times that guess. And we'll call that result x1. Then we will try again. We will take the x1 when we find out it wasn't close enough, and we will square it and add a again and divide by 2x1 and come up with x2. Each time we will check x2 by squaring it and see how close it is to the number a. And we'll keep doing this over and over again until we are satisfied that we're close enough through direct checking of the square of the solution. So perhaps by the time we get down to the 4th value, we get something close enough. This happens to be a very good way to calculate square roots. Try this yourself. Try the square root of 5 or the square root of 20. Try different numbers and use this exact same algorithm and see what result that you get. So what did you think about the pseudocode on the previous page? It seemed very repetitive to me. It seemed like I was writing the same kind of formula over and over again. Perhaps we could improve on that by coming up with some looping syntax in our pseudocode language. We also need to have an idea of a stopping rule, or what we will call a tolerance in this case. Now I want to draw your attention here to this left arrow. What that arrow means is assigned to. I am going to go into memory of the computer and go to a location which I'm calling tolerance. Tolerance isn't really a variable at all. Tolerance is just the name of an address in memory. It's literally a memory location. And I am asking the computer to take the number 10 to the minus 10th and store it into the memory location whose address is called tolerance. Now I want to set up a kind of a loop. There is a while loop that will cause code contained in the while loop to repeat until this particular logical condition is no longer true. As we check it, as we come in and check to see if error is bigger than tolerance, initially, of course it is. 1 is a lot bigger than 10 to the minus 10th. I take this x, which by the way currently has the value 1, and I am going to assign it to yet a new variable called prev, or previous. Then I will use this computational formula you saw on the previous page and overwrite the contents of the memory that is named x. Now I said that carefully. This x down here is the same as everywhere else I have an x, only in the sense that it's the same address in memory. I can keep changing the contents of what's in the memory, but the memory address is always the same. So what this statement here says is go back and find the x that's already there. Well, right now that's 1. Square it. Add a number called a, which I would have had to supply to this algorithm, and then take that quantity and divide it by 2x. After that operation is done, then overwrite whatever is in the x location, whatever memory location that x points to, overwrite that data with the new value I've just constructed. Now, conveniently, the step before, I preserved the contents of what was in x into this variable called prev, and that gives me the opportunity to take the difference between the new calculation and the previous one. I'd like to call this a progress measure of how much movement did I get in x relative to the previous calculation. We'll take the absolute value of it, so we always get a positive result, and we will overwrite what was in the error variable. We're done, and so we'll end the loop, but what really happens is MATLAB will come back up to the top, if this were a MATLAB program, and it will now check to see if that new error that I just constructed is bigger than the tolerance. It probably will be, and since that's likely, we will come down and do the exact same calculations again. But notice the value that's in x is actually the reconstructed value. It's what I called x1 before. And after I do the same computation and restore it in the same location, logically it's what I called x2 on the previous page. And if this algorithm is doing what it should, then the x and the previous value of x are getting closer and closer together until finally the difference, which we're calling error, falls below the tolerance. In other words, the 10 to the minus 10th. When that happens, my algorithm is done, and I have determined the square root of the number a. That is one of the ways that we can do a stopping rule. There are others, but that's one. This one has some risks that we'll talk about later in the course. But this is the fundamentals of an algorithm that will compute square roots. So let's suppose we ask another question. Could we program the following expression? Now this has nothing to do with roots. This is just simply, can we evaluate a polynomial for a particular value of x? Well, let's go ahead and give it a try. Now this time I'm numbering the code just so I can refer back to numbers. You don't need to do that on your actual code. And so I'm pre-declaring two integer values called I and n. And we're going to also declare two other variables called p and x, but these are going to be real. They will be stored differently than the integers. We're also going to pre-allocate an array called A. It will have the ability to store n plus 1 values, A of 0, A of 1, up to A of n. These are going to be the same as the subscripted A's that we're looking at in the P formula. We want to evaluate P, and so we will define it initially to 0 and then start doing another loop. This time the loop is called a for loop. And we will send this integer from 0 all the way up to n, that is walking through the indices of the A elements of the A vector. Inside that loop, we'll take whatever value of A of I that we have, in this case on the first pass we're talking about A of 0, and we will multiply it by the ith power of x. Now, you may complain here that you don't know what A is and you don't know what x is, and I think I would complain about that too. In pseudocode, you don't worry too much about making your code totally complete. You're trying to use this language environment to get the bugs or get the thought process through on your logic. That would then finish this whole algorithm, because as we are going through this loop, we are starting off with 0, and on the very first pass, we would pick up A of 0. That's going to be the constant term that we have, and we would take something to the 0th power. Well, that's always going to be 1. And we'll add it back to 0 because P was initially 0. So all this first step really did is pick off that first coefficient. Then as we come back around again, we will take the next coefficient, A of 1, that's this guy here, multiply it by x to the first power, well, that's the same as x, and then add that to what we had before, which was A of 0. So now we have accomplished in getting the linear portion of that polynomial. And then we would just continue this loop, picking up the x squared term, the x cubed term, and so forth, until we were done. So let's talk a bit about code structure. In MATLAB, you'll often see terms like this, 0:n. What it really means is it's setting up a vector containing 0, 1, 2, 3, 4, up to some number n that you have to define in advance. And the for loop is incrementally assigning those values to this looping variable I. The I value can be used as a parameter to some of those arrays that are in there and continue to run until the loop is over. Okay, so on your MATLAB loops, something to note, MATLAB does not like starting loops with 0. That's very unfortunate because most algorithms do start with 0. And so what I recommend you do is write your pseudocode as close to the math as you can, including loops that might start with 0. And then when you write your MATLAB code, you might have to make some adjustment to allow the looping to do the same thing, even though you have to start with 1. Each iteration that we have will update memory with new values. And again, we've mentioned this already, but a variable name is just the address of a memory. And then this is really key. You know, in today's world, we think computers are so fast and memory is so cheap that it really doesn't matter if you're sloppy or not. In this class, it matters. I fully expect you to have efficient code that could be used in a very tight loop of some engineering process and not slowing down the calling program. So don't ever rely on computing power to make up for sloppy programming. Okay, so it's time for another homework. What I'd like you to do is prove that if you have an arbitrary number of odd integers, then the product is odd. That's one direction on this if and only if statement. Or if you go backwards and say the product is odd, then prove that every integer must be odd. So that's what we mean by a if and only if statement. It works both ways. After you prove that, write the pseudocode that forms the product of the first n odd numbers. This is one of the few times you will turn in your pseudocode. Most of the time you won't, but since it's part of your homework, we will on this one. And I'll let you look at these hints yourself later. As you get the PowerPoint for this, you can take a look at this, but there are some hints there that help you face this thing. Okay, so we'll hang it up here, give you a chance to try your hand at this first homework assignment, and we will see you next time.